Find the equation of the tangent plane to the surface, x squared minus xy minus y squared minus z equals 0 at the point 2, 1, 1. So we want the equation of a plane. I need two items. First, we need a point. That'll be 2, 1, 1. Then I need a normal direction. This is going to be a vector that's perpendicular to the plane. To get that, I'm going to have to rethink the problem. So we're going to define a function, capital F. It's going to be a function of three variables, x, y, and z, given by x squared minus xy minus y squared minus z. Then you'll note our surface is just going to be where capital F is equal to 0. So it's going to be a level surface. Then we know that the normal direction to a level surface is just going to be given by the gradient. So we need the gradient. Okay, our gradient's just going to be given by taking capital F, take the partials with respect to x, y, and z, we load them into a vector, and then we evaluate at our point 2, 1, 1. Okay, that's going to give us a vector. That's our normal direction. So to get the equation of our plane, we're going to take the three numbers that come out from our gradient, load them up against x minus our x0, y minus y0, z minus z0, set it equal to 0. Okay, and our x0, y0, z0 is just our point 2, 1, 1. So this is just the dot product definition of the plane. To get our gradient, we need to calculate the partials with respect to x, y, and z. So let's do partial with respect to x. So the idea is x is our variable. We treat y and z as constants. So we're going to get 2x minus y. Then I put in our point 2, 1, 1. That's going to give me f partial with respect to x is equal to 3. Do the same for y and z. So partial of f with respect to y. Y is the variable. X and z are constants. I get minus x minus 2y. Put in 2, 1, 1. I get minus 4. And then for z, notice we only have one term with the z in it. So take its derivative, we get a minus 1. And then whatever I put in for our point, we get a minus 1 out. So that's that. Our normal direction is going to be 3 minus 4 minus 1. So I'll load them into the equation of the plane. So 3 minus 4 minus 1. And then we put in our x minus x0, y minus y0, z minus z0 terms. Okay, so that's 2, 1, 1, set it equal to 0. When I collapse, I get 3x minus 4y minus z equals 1. We could check, we could put our point into this, we better get a 1 out. So I'll get 6 minus 4 minus 1 gives me 1. So that checks. Now, we'd like to check our normal direction. So in this case, we can do it by solving the problem in a different way. If you'll note, we have z all by itself, so I can push it to the other side. I can think of this instead as z equal to a function of x and y. And then I can solve this by doing our tangent plane equation in two variables. So what happens there? So we have the function z, or f of xy, okay, and this is small f, x squared minus xy minus y squared. Our point's going to be xy equal to 2, 1. Then we take the partials with respect to x and y. So they'll look familiar. We'll get a 3 and a minus 4 out when I put in 2, 1. And then to these numbers, we're going to associate the vectors 1, 0, 3 and 0, 1, minus 4. If I want to get the normal direction of the tangent plane, I take their cross product. To get that, we load in I, j, and k, put our vectors in, and then we're just going to do this crisscross method that we learned for cross product. When I do that, I get minus 3i plus 4j plus k, which gives me the vector minus 3, 4, 1. Now, that's going to be our normal direction. If you note, it's not the same vector we got before. Before I got 3 minus 4 minus 1, But we're safe because the normal direction can be any vector that's perpendicular to the plane. If, for instance, I take this vector, the vector that's coming out is just -1 times that vector. So if this is perpendicular, then so will be this vector here. So this checks our normal direction.